Assalamu alaikum everyone. This is Muhammad Ibn Shihab Shad. Now I will discuss the MaxFlow algorithm with you. The MaxFlow algorithm. So we know that the MaxFlow algorithm is used in linear programming to maximize the flow and maximize the flow capacity from the source to the destination. Okay, so to understand MaxFlow, we should draw a graph like the source to the shrink. Okay, so here the main goal is to transport goods or elements from the source to the shrink, and here in between many nodes or vertices is present like this, and our goal is to send the maximum amount of products or goods via these in between nodes. Okay, and here from source to like point A there is a channel, and the channel has a capacity. Suppose this channel has a capacity of 10. So here these all are also connected as well, and they have these capacity. Okay, like different way they may be connected, and they are always directional graph. Okay, so and as they are directional graphs, so we have to follow this direction wise, and like suppose we can go from S to A, we can go from A to B, we can go from C to B, but we cannot go from B to A or B to C. This is one of the constraints, and the main constraint is like the limit of each channel. So suppose let us assume that with a pipe, a water pipe. So here this is a water pipe, and suppose the water pipe have a capacity to flow 10 liter water within the pipe, and we can flow the limit, the water which is less than this limit, but we cannot flow or we cannot overflow this limit. Okay, this is the main constraint here and this is applicable for all these joining paths, for S to B, S to C, A to D, B to E, and all these. And now the goal is to maximize the flow, and for this we have total 3 algorithms. One is the Fulkerson algorithm, second one is the Edmonds-Karm algorithm, and the third one is the Dinic algorithm. So in this example we will understand that what their working process, first their working procedure, their time complexity, and their space complexity, that means their computational complexity, their advantages and disadvantages, and when we should use these and what are the criteria of using these techniques. So let us start with the Fulkerson algorithm. So for that we will consider a very small graph A, B, C. This is the source, this is the shrink. So suppose this limit is 10, this is 5, this is also 10, and this is 10, this is 7, this is 8. Suppose this one is 5 and this one is 4. Okay, not consider this as 4, this one is like 2. Okay, now what about the fourth Fulkerson algorithm? The fourth Fulkerson algorithm selects the path combination randomly and augment this again and again until it satisfied all the constraints. Suppose, like for fourth Fulkerson, if we start with S, then S to B and B to T. Here we have to first compute the bottleneck value. So what is the bottleneck value here? Here the bottleneck value is 7. So in this path we cannot exceed the flow more than 7. So from S to B there will be like 7 by 10, as we have flowing this amount, and 7 by 7, this is a maximum flow, and here 7 unit will be transferred from S to T. Now this one is completed, this path. Now like here from S to B, here we have still remaining 3 units. Okay, so S to B we have still remaining 3 units, and here we can go to B to T, but we can go to B to A to T. So if we do this like S to B, B to A, and A to T. So here in this path we have limit S to B, here is 3, as because we have already passed 7 from it. B to A is 2, and A to T, that's 10. So here the bottleneck value is 2, so we can flow 2 units from here. Okay, again this and this one is our first iteration. Like first this one is first, then this one is second, then we have flowed from here to here. If we consider the third, from S to A, A to T, so here we can see that from S to A we can maximum flow 5 units, and from A to T we can maximum flow 8 units, as because we have already flowed 2 units from here. So in third iteration we will like S to A to T, and this will be like 5, and this is like 8, and bottleneck value is like 5, we can 5 unit. So till now our total is 7 plus 2 plus 5, which is 14 units, and we have to do this again and again until we reach all the limit and we have satisfied all the constraints, and like after that we can flow from here to here, that will be 8. From S to C, so like S to C to T, we can flow 8 units, then it will be 14 plus 8, that's equal to 22 units, and finally we can flow the remaining 2 units here from S to C, and from here we can flow S to A, that's like 5 unit is total applicable, but we have only 2, we can flow this one, and from here we have passed here S to A to T. Like first we passed 2 units, second we passed 5 units, and we have remaining 3 units, so we can flow 3 units from A to T. And what we want to flow from here, that's we have 3 units, but we want to flow 2 units, so we can flow the 2 units from here, so another 2 will be added here, so total will be 24 units. And here we can see that the complexity depends on what? Complexity always depends on the vertex and the capacity. So the vertex and the capacity is applicable for this. This is its complexity. And now if we move to same problem with same problem, and for Ford Fulkerson algorithm, Edmonds-Karm algorithm. So Edmonds-Karm algorithm is also one kind of Ford Fulkerson algorithm, but it's used the breadth first search. So it was like our graph, like ABC, sorry for the mistake, and T. And same value 10, 5, 10, 7, 10, 8, 5, and that's 2. So for this one, the Edmonds-Karm, we applied the breadth first search. Okay, so what actually happens here in BFS, that is, first we start with S, and after S we have like the S, the adjacent of S is like B, A, and C. Okay, so now while we move from S to like B, the adjacent of B is like A and T. As because of A is already traversed, so we go to T, B to T. So S to B to T, and after traversal of tree, none of the vertices remain, so this will be the first one. Okay, again, so here it's the same, like the bottleneck one is 7, so 7 unit will flow from here, and after that we will again start with S. Now we have remain A, and the the adjacent of A is T, so S to A to T, that is like 2 units, that is 5 unit. Okay, now again the S to like C, and the adjacent of C is A and T. A is already traversed, so we will start with T, S to C to T, that's 8 units, so total 20 units till now. Now like from S to B to SAB and C, BAC, like this one is traversed, this one is also traversed, this one is also traversed, and B to A and T, this one is traversed by this S to A is already traversed, but B to A it still remains, so B is to B to A to T. Okay, same as like S to C to A to T. So here 2 units, total 4 units, so 24 units. Okay, here it was like the BFS was applied in Edmonds-Karm algorithm, and we have got the same number of MaxFlow here in using BFS. And here, due to using the BFS, we can see that like the complexity remains like vertices and edge square depending on the edge. Okay, now now it's time to analyze the Dinic algorithm. So in the Dinic algorithm, what actually happens like is like same, suppose this is sorry, like this is B, A and T, same graph, same, all thing are like same, but in the Dinic algorithm, it's first apply the depth first search, then the breadth first search. So it always apply the DFS and the BFS. Okay, here if we traverse like if we go to this, then if we like do after traversing, as this is already traversed by the in first iteration, here if we come here, if you notice this one, like S to B to T, as because of A already traversed, that's why we didn't move to S to A here. But what we might do that, as S we can go S to B, then B to, as B to T already traversed from here S to B, this one I am talking about if this is the first iteration and this is the second, like S to B, B to T is already traversed, B to A is not traversed, and B to A to T. So this is also correct for the Edmonds-Karm algorithm according to the breadth first search, BFS. So this might be our second step, and after that this might be our third step, this might be our fourth step, and this particularly this one might be our fifth step, and we can still got the the total max flow is 24 units. But what is for Dinic algorithm? First it analyzes the depth of this, like first as the source is it is the source and the destination is T, so it will go first S to B, B to T. Okay, and here in the Edmonds-Karm, the step 2 is not allowed here in Dinic algorithm. We can't apply, if this one is our first one, we can apply this one like S to B to A to T as the second one. We can't apply this as because it goes first depth first search. So here if this is the stage 1, this is the stage 2, this one is the stage 2 as well, and this is the 3, so it is not allowed here. Okay, so if we go through, if we apply the Dinic algorithm, we have to go through this first. This is must. First these three steps, then we can apply these two. And due to explain that, I have written it here so that I can explain you that in Edmonds-Karm algorithm we can directly go through this, but in Dinic algorithm we must go through this, then this too. Now its complexity is like vertices square into edges. Now you may ask me that why we are applying this, and the total max flow of this will be 24 units as well. So you might wonder that why I have done these things and they have same number of maximum flowing capacity but different technique, what their relevance and when we have to apply which method. So first, and what is their limitations as well. So first, if we go to the Edmonds-Karm algorithm here, this one, let me draw it in green. So here is a one simple example I want to explain you. Suppose this is 100, this is 100, this one is 100, this one is 100, sorry, this one is like 99, this one is like 99. Okay, and here is like two-way path from A to B and B to A. This is one, this is one. So if we apply Edmonds-Karm algorithm, then we can see that from the image, like from the image we can visualize that if we go this and this and this and this, then we will be achieve maximum flow at once, and after that if we go through this and this, then it will be like easier one, we can flow this easily. Okay, but we can say that as we are visualizing this one. Okay, and the algorithm does not works like visualization. Okay, so where if we apply the Edmonds-Karm algorithm here, it might select S to A to B to S to A to B to T. Now you may wonder that why like this one is important, or you can check its relevancy as well. So now if S to A, that is it is 100, A to B this is 1, B to T this is 99, and the maximum flow from it will be 1 unit. Okay, and then again S to B and B to A to T, this will be 1 unit only. So as this is the algorithm is not visualizing this, in worst case it may happen that only 1 unit of product you are delivering from source to destination in first iteration, in worst case like this. And this may, and we know that maximum flow algorithm and linear programming, combinatorial optimization, we try to maximize the profit. So if we apply this, the profit wouldn't like maximize firstly. While we will complete this, that will be maximized, we know that, but initially it wouldn't. So it is the problem of the Fulkerson algorithm, as because the complexity of Fulkerson is depends on the capacity constraint. Okay, this one. And now we will go to the Edmonds-Karm. If we go to Edmonds-Karm algorithm, like now first we will discuss where it should be applied. In such graph where the depth is not that much, the Edmonds-Karm is suitable for those scenarios. But if some graph has like depth it has higher depths like S, A, B, C, D, E, F, G, H, T. Suppose this is 10 units, this is 7 units, this is 2 units, this is 1 unit. And from this is also 1 unit. Sorry, this is suppose 10 unit, but this to this is 1 unit, this to this is like 10 units. Okay, and this also 10 units. For so I have used 10 so that I can explain you easily. So suppose as Edmonds-Karm work like, and these are also connected. Okay, these are also connected like this, and so on. So first, if we we apply the Edmonds-Karm and apply the BFS, then first we will start from S, and the adjacent of S is like A, B, and C. Now we took the A, and the adjacent of A is like B, D, E, F. Okay, as because of B is already traversed, so why not like let it be 20? Why not we start with like wouldn't traverse that, as because of this is already adjacent to S. We will start with like D. From D, the adjacent of D are like E, G, and H. And here we can see that E isn't traversed. Okay, E. Okay, if we remove this, like A to E does not have any connection, so we can see that D to E have a connection and E is not traversed till now. So like S to ABC, S to S, S's adjacent is A, B, and C. S adjacent are B, D, and E. As because of B is already traversed, so we will start traversing D, and the adjacent of 1 minute. The adjacent of D is like EGH. E isn't traversed by A, that is as because of E is not adjacent to A, then we will traversing E. E2 we will traverse, E's adjacents are like G and G to T. So the final traversal may A is to A to D to E to G to T. So this one is a correct traversal, right? This one is a correct traversal, and here we can see D2 is like 1. This follows the BFS, and this is not wrong. This one is correct, but like 10, 7, 1, 10, 10. Okay, this one is like this, and maximum flow will be from here like 1 unit. And if you design a logistic channel for a region or or your nation wise, then it may have S to multiple district, then here district to other multiple one, they are interconnected, and from here the next one will be. So if you design your logistic for your nation wise, it may have a very depth graph. Okay, and suppose these are points, they are connected. So they are interconnected, they are hierarchical and very much interconnected, and this one is like correct, this one is correct example, and this one is correct flow according to the Edmonds-Karm, according to the BFS. But while you are applying these for the depth tree, the tree has many very huge depth. That time the Edmonds-Karm failed, as because of, you may see that, you may notice that here the number of vertices are lesser than the number of edges, as because it is a depth tree. So like from, if we design a thing like C to F and S to C to F, F to E, then E to G and T, so there will be one unit as well, and this made the Edmonds-Karm complex during the depth wise tree. So we have seen that Edmonds-Karm is suitable for those tree who does not have a longer depth. Now time to work with the Dinic algorithm. Like we will go with Dinic algorithm for this same curve. Dinic algorithm work like depth first search, then breadth first search, DFS, then BFS. So this is not allowed for the Dinic algorithm. Why? As because they have the same depth level, so this is not allowed. So S to A, A to D, D to, like D to E is their adjacent and non-traversed as well, but they have the same depth of 3. So instead of traversing E, D will rather traverse G or H, then T. So suppose it traverses G, so S to A to D to G to T, then here the maximized flow is possible. So the Dinic algorithm works better for these depth-wise trees, as first is it will traverse all the paths that are free from there, the goods or products can be flown, and with a different depth, like maintaining the depth like 1, like 0, 1, 2, 3 and 4, like this is 0, 1, 2, 3, 4, and after traversing this order, when this order is complete and we cannot flow anymore with this order, then it will go to like a 3 to 3, then after completing this one, then this one is applicable for Dinic algorithm. Okay, so after what I said earlier, that after traversing this depth wise it can traverse like this, so it will maximize the flow. I mean that the maximized flow will be remain same for Dinic's algorithm, Edmonds-Karm and Ford Fulkerson, but the complexity matters. Here it is less complex than the Edmonds-Karm or the Dinic's algorithm. So it was about the MaxFlow optimization. I hope you have understand this, and if you have any question regarding this, please comment below. Thank you.